Alright, so let's go ahead and give number 3 a shot. Hopefully you've got some start on this problem, but if you got stuck, let's go ahead and give it an extra go around. So as we look, first thing we have got to do is write a balanced equation. As we look at our reactions, we've got gaseous ammonia over copper to oxide. The other products are nitrogen gas, solid copper, and water vapor. So we've got two reactants. We've got NH3 reacting with copper 2 oxide. That 2, if you remember, indicates the charge on that copper. So we're going to have Cu with a 2 plus charge. Oxide, if we find oxygen on the periodic table, that's O2 minus, 2 plus, 2 minus, solid, viable compound. They are going to produce the products nitrogen gas. Remember that nitrogen, Hofbrinkel, nitrogen is diatomic. Also produced would be our solid copper and our water vapor, H2O. So the first thing we do when we have a balanced equation problem is we write all of our products, all of our reactants, make sure they're all stable. Check. Done and done. Next thing we do is we go back and we check our state symbols. We put them all together, plus signs, arrow signs. Check your state symbols when we pass gaseous. All right, so G on the NH3 over solid copper 2 oxide. We get nitrogen gas, that's another G, with solid copper, and water vapor. Well, vapor, that would be a gas as well. The very last thing we ever do to conserve our mass, law of conservation of mass, would be to go back and make sure we've got viable sides on both sides of a reaction. We've got a conservation of mass. So if, let's pick an element. Let's do nitrogen. 1 nitrogen on the reactant side, 2 on the product side. So we're going to need 2 on the reactant side, 2 nitrogen, 2 nitrogen. Now we have 6 hydrogen. Oh, so we're going to need to multiply this side by 3 to make 6 hydrogen. That makes 3 oxygen. Go back over to the reactant side. We've got 3 oxygen. Make it a 3 for that coefficient. That makes 3 coppers. We then need to have 3 copper on the product side. Alright, if we check, both sides are conserved, same number of atoms on both sides, so the mass has to be the same. Okay, so balanced reaction. We know what's going to happen when we go to add our reactants together. Now, here's the trick, here's the problem. They told us that we've got 15 moles of our ammonia, and we're adding that to 15 moles of our copper 2 oxide. Now, one of these is going to run out first. One of these things is going to not be enough. One of these things just doesn't belong. Okay, so one of these is going to run out first. We got to figure out which one. And it could be either one. Our way to figure that out is to figure out which of these two, either the ammonia or the copper 2 oxide, makes the least amount of product. It's just the one that runs out first. So when it runs out, reaction stops, is finito, makes the least amount of product. Well, let's pick a product. Does not matter which one we pick. Why don't we pick copper? Sure, why not? We can solve for any product. The only trick, the only key is that for both of these, we're going to solve for the same product. So what we're going to do is we're going to change from moles of our 2 starting substances into moles of copper. We're going to change them both into the same product because then we can compare them. Well, okay, it's just game dimensional analysis. We're in moles of our first substance. We're trying to get into moles of the second substance. To get from moles to moles, we use the mole ratio. In this case, the ratio is 2 to 3. Our NH3 is on top right now, so we're going to put our 2 moles of NH3 on the bottom for every 3 moles of copper on top. Well, 15 times 3 is 45, divided by 2. 45 divided by 2, what is that? Oh, I don't know. Alright, let's try this again. So 45 divided by 2 actually gives us 22.5 moles of copper. So if all 15 moles of our NH3 ammonia react, it's going to make 22.5 moles of copper. Now, we don't know if it's going to make that many. We got to look at our other reactant, our other piece of the reaction, our recipe, if you will. Well, we're in copper 2 oxide. Try to get to moles of copper. We're going to use our mole ratio from the balanced equation. In this case, it's a 3 to 3 ratio. If our moles of copper 2 oxide are on top right now, we're going to put our moles of copper 2 oxide on the bottom in our next step. For every 3 moles On bottom, we have 3 moles of copper on top. Moles of copper to oxide cancel. 15 times 3 gives us what? 45? 45 divided by 3 gives us, 15. So, here's what we just discovered. If all 15 moles of the NH3 react, they can make a total of 22.5 moles of copper. If all 15 moles of the copper to oxide react, we can make 15 moles of copper. But when we make this reaction go, we actually use both of these reactants at the same time. And one of them runs out first. One of them limits our reaction. It is the one that makes the least amount of product. So this is an important piece of information. That little small number right there tells us that, in fact, this copper 2 oxide, CuO, is the limiting reactant. Ding, 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 ding. Awesome. It's the boss. If we had to do any other calculations, if we had to figure out any of our products, we would always start with the boss. Cool. There's the second one. You go ahead and try number 4 for me.